particles. And pretty strong University of Munich. And that's focused on the game theory.
Yeah, thanks for introducing me and thanks for inviting me here.
Microphone.
Do I need it? Yeah. Am I on?
There are two switches.
Now?
Yes.
Hope I'm not too loud. So thanks for inviting me. It has been a wonderful time here. I don't know whether I can teach you games. I saw yesterday that you were playing this beer pong, I think. That's a game which people like, it seems. So the idea of this talk is to teach you about evolutionary game theory. And what it really is, it's about non-equilibriums and non-dynamics in interacting particle systems. I'll give you a short outline of what I'm going to talk about and how I'm going to structure my lectures. Today, I will mainly give you an introduction into game theory, and I use that introduction into game theory to also teach you something about nonlinear dynamics, some elementary concepts in that field. I would also like to give you some examples from biology where game theoretic ideas do play a quite important role. Then my second lecture tomorrow, that will be on a particular game theoretic model, which is called the May-Leonard model. And I will use that model as an example to teach you advanced techniques in nonlinear dynamics. They will turn out to be very important because those concepts also enter, if you're interested in studying the spatial dynamics, they will need the results obtained in the second lecture. Yeah, in the third part then, on Friday, I will get to spatial games. So let's get started. Game theory is actually a quite old subject. Those are not really the most ancient founding fathers of game theory. The first one is Emile Borel. He was motivated by playing poker to think about strategies, and obviously about strategies which are the best strategies in order to win a certain game. But these people really put things on mathematical grounds. There are two important developments. One is by Nash, the other one is by Maynard Smith and George Price. In the first development, Nash was thinking about more or less social settings with rational players, where the rational players would try to play the game such that to have the largest profit they could possibly get by playing it rationally. And he defined what's called the Nash Equilibrium, and he said it's reached as soon as no party can increase its own profit by unilaterally deciding differently. We'll see what that means. In a more biological context, Maynard and Smith actually talked about equilibria in game theory as evolutionary stable if a population of individuals playing that particular strategy is able to outperform or eliminate a small amount of any mutant strategy which you would introduce into the population. So the point is here, you cannot be invaded by somebody else if you're playing a particular strategy. So those are the two concepts, and let me explain them on a very classical example. The most classical example of our game theory we can find is the so-called prisoner's dilemma, and that prisoner dilemma is formulated as follows. You have two suspects of a crime, and they are arrested by the police. The police has insufficient evidence to really to really convince them, or to really put them into prison for the major crime they have committed. So what they do is they put them into two different rooms where they cannot communicate, and then they would question them. And it goes like this. So if one suspect actually testifies against the other, so he betrays the other, while the other one doesn't say anything, then the one betraying the other gets free, and the other guy actually is worse off. He gets 10 years of prison. So that's one scenario. The other one is that actually both of them testify. Then they can find out about the major crime, and they would be sent to prison for 5 years. If both of them keep shut, don't say anything, then the police is unable to really prove that they have committed a major crime, and they only jailed for the minor crime. So they're sent to prison for 1 year. So that's the game, and the way you put it mathematically is actually in terms of this payoff matrix here. It makes it a little clearer what's meant by this. So you have two suspects, a player 1 and a player 2. So you have a row player and a column player. And say you put yourself into the position of this player 1 here, and then you decide rationally now what kind of strategy you would like to pick depending on the choice the other player makes. So let's try to play. Yeah, sure.
I'm not quite sure. So if I read this as a matrix, so say for instance I take the CD term, so that what I sort of I miss what the other player
Okay,
gets.
good question. This is a symmetric game.
Uh-huh.
If you know the outcome for one player, you know the outcome for the other player.
Uh-huh.
Okay? Because
So-
it doesn't really matter whether you player 1 or player 2.
So
If you want to put it
yeah.
as a payoff matrix for both players, what you can do is you can have the first entry here as the payoff for this player here, and you could use the second entry here as the payoff for the second player on the top row.
Okay, so if
So you will put here 1 year, comma 1 year.
uh-huh.
You put here 10 years, comma 0 years.
Yeah.
Here 0, comma 10, and here 5,000.
Right, and that's how I should interpret
Yeah.
this, right? So
And since it's symmetric-
CD is 10
Yeah.
means the
So what's here is the payoff for this
Yes,
player
yeah.
here. So I'm playing these two strategies
Yeah.
against this guy here, and this is my payoff if I'm encountering the different strategies of player 2.
oh, okay.
And now I can reverse the thing, and then it's symmetric.
Okay, so it's the playoff. The payoff that's listed here is the payoff corresponding to the column.
Yeah, to the column player, to
Yeah.
player 1.
Okay.
Thanks for asking. Yes?
The column is there. The column is what is column?
So you are player 1, and you have two strategies. You can cooperate, or you can defect. That's player 1. Player 2 is here on the row, and you also have the same kind of strategies, cooperate and defect.
And the entries are matrix of payoff for player 1.
Yeah, okay. And I'm going to it now in detail. So let us say that player 2, so that's you all, are playing to cooperate. And I'm player 1, and I have to decide, under the condition of what you are playing, what my best strategy is. So I look at my payoff matrix here, and I see if you are cooperating and I am cooperating, I get 1 year in prison. And obviously it's for me much better to betray you, then I get freed, so I have 0 years in prison. So my choice, if you play cooperate, is I play defect. Okay? Now,
I'm
Yeah.
sorry, can you just repeat what does cooperate and defect mean in terms of testifying?
see, for the prisoner, to cooperate means that you both don't tell the police anything.
Okay.
Right? You keep your mouth shut. and that means to cooperate with the other guy. And betray or defect means that you testify against the other person.
Thank you.
Yeah? Good. So now let's say you are playing a different strategy. You are defecting, so you betray me. Then I could also play to cooperate or defect. Now it would be stupid to cooperate, because then you get free and I get all the prison. I get 10 years in prison. So again, for me it's better to defect, because then I'm 5 years in prison, and it's better than being 10 years in prison. So really, independent of the choice you make in that game, my best choice is always to defect. And since we're all rational people, we analyze the game in very much the same way, so we all come to the same conclusion, so we all defect, and the outcome of the game is that we both play defect, and we both go to prison for 5 years. That's of course the dilemma, right? Because we would be better off if we would have cooperated, and then we would just be sentenced to prison for 1 year. And that's behind most of social dilemmas, that to defect here actually is a large temptation, since playing against somebody you're always better off by defecting. This equilibrium here, both defecting, is a Nash equilibrium, and you see why it's called a Nash equilibrium. If you deviate from it unilaterally, then you can only deviate to this point or to that point, you're worse off. You would need to deviate from that equilibrium bilaterally in the direction of diagonal, and then you would be better off. Okay?
Shouldn't you assume that this player is definitely a cooperator, because then at most you get either 1 or 0?
Pardon?
Shouldn't you assume that the other player is definitely a cooperator, because then you get either 1 or 0 years, based on this game?
I don't get this. I don't get this.
I guess
then the other player gets 2 years.
I guess it was.
You don't know what the other person is doing.
Yeah, you don't know for sure.
But thinking rationally, you know that they're going to do that.
Yeah, that's the point.
So your choice is, are you going to cooperate or defect? And if you change your decision to cooperate, now you're worse off. So you can think rationally and you also.
If you play this game actually with real people, that's not the outcome. Real people decide very differently because they have experience and they think they're going to play this game more than once. Yeah? Okay.
But if it's a finite number of times and you know the number of times, then it's always better to do that.
Yeah.
If you know you're going to play every time.
There is a way to analyze this game if you repeat the game and see it.
So that's based on don't trust the other person.
Yes, be rational.
But even if you trust the second guy, it always makes sense to defect.
Yes. Yeah.
Right?
Whether your game might go against you.
Good. So we can discuss about this and see. Now, to put the game a little differently, more on the positive side, this here actually was a cost matrix, not a payoff matrix. You don't gain, you lose here. So let's put it in terms of a payoff matrix and in terms of benefits and costs. So then you can formulate the game such that if you cooperate, so this is the payoff matrix of this guy here, then you actually pay a cost, C, that's on the minus side, and you also get a benefit by doing something. And you assume that the benefit is larger than the cost, so that entry here is positive. If you're a defector, then if you're facing a defector, then you only pay the cost because the other guy is not cooperating. And on the other hand, if you are defecting and you meet a cooperator, you get the benefit, but you don't have to pay the cost. And if you both defect, then nobody gets anything and nobody pays anything. You can generalize those games actually into a very general setting of 2-player games. where you would have these 4 entries. You would have one entry being a reward if you both cooperate, the other entry being a punishment if you both defect, and then if somebody else is cooperating, then you are tempted to defect, and your payoff is the temptation T, and the other guy then gets the sucker's pay. So that's the general formulation of the game, and if you analyze it, you see that only 4 different types of games you can play if you're in such a general 2-player setting. Let's look at one game which is actually interesting because I'm going to talk about it in a biological setting. It's called the Snowdrift game, and the Snowdrift game is different from the Prisoner's Dilemma game by this entry here. Here it was the case that if you're meeting somebody who is defecting, it's better for you to defect actually. Here's the reverse. If you meet somebody defecting, for you it's better for you actually to cooperate because the payoff here is larger. Let me explain that in a more visual way. Snowdrift game, you can play this in Colorado. At winter, you are caught in a snowstorm. Your car is behind a huge snow pile, and 2 of you want to get out of that snow pile. And you have the option of shoveling the snow or not shoveling the snow. If the other guy is shoveling the snow, you're better off not doing anything because you get out for free. If the other guy is not shoveling the snow, you should do it because otherwise you both might freeze to death. I've learned that this game is also played here. I would call it backpack game, where the question is, going hiking, who is carrying the backpack? But it seems there's an asymmetry between male and female. Okay. So here the interesting observation is you have actually 2 types of equilibria, because for you it's always better to do the opposite of your opponent. Right? So if the other one is defecting, it's better for you to cooperate, so you're here. If the other one is cooperating, it's better for you to defect. So that means you have 2 types of equilibria. That's in the game theory context called a mixed Nash equilibrium. We will see later that in the context of non-dynamics, this is a bistable system, whereas the Prisoner's Dilemma is a monostable system with 1 fixed point, and this one here with 2 fixed points.
Excuse me, does that assume that C is greater than B, so that that's the right, so that B minus C is less than 0? Or?
I was always assuming that your benefit is always greater than your cost. So B is always greater than C in both cases. So this entry here is positive while this one is 0. So you're better off here in cooperation. Okay. So evolutionary game theory is a bit different. The way we talked about this was in terms of being rational and making certain decisions based on the complete knowledge of the game. This is not true, even in society, but it's especially not true for a biological setting. In a biological setting, the game one is playing is very different, because the strategy actually is some kind of program running in an entity, say a bacterium, and the bacterium is fixed to that program and fixed to that strategy time after time after time. So you cannot change the strategy in a biological setting. But what you can do in a biological setting is that if you have a population of individuals, the relative number of individuals playing a particular strategy can change over time because some die and some get born. Yes?
Are you allowing mixed strategies where you play one thing 0.6 fraction of the time?
Thanks for asking. That kind of thinking of playing a game with a certain probability belongs to strategic games. Here in a biological setting, you play the game for sure if you are an individual of a particular type. But they both are related. Think of a box of individuals, and this box is well stirred, and then playing a particular game depends on the number of individuals you have in that particular box, and that's as if you would play a strategy with a certain probability which is equal to the relative frequency of individuals of that strategy in that box. So that they're related, but the way to think about them in biology is different. There you need to say that a particular individual is playing a strategy always. Okay? And the driving forces, as I said, in biology are things like selection, birth, death, mutation, those kind of things lead to changes in the relative frequency of certain strategies in a population. So we automatically geared towards studying population dynamics.
So yes. There's no possibility in this framework of sort of feedback for the strategy, like to say more.
Pick up this.
There is no possibility of sort of feedback in the strategy, like if you're trying to model like more complex organisms or intelligent organisms in some way.
Of course, there is feedback in the following sense. So imagine you have bacteria, and they are spreading some kind of pheromone. This pheromone then gets transmitted into the fluid and can be detected by other bacteria. This then triggers certain biochemical reactions in that bacterium, which then leads to maybe a change in the strategy of that bacterium. So that can happen, and that's part of that scenario. Okay? And I would call that mutation or just another species in the game, which then adds to the complexity of the game. So in essence, you're studying population dynamics with a certain population size, and you have individuals of different types I, and you have a number ni of those individuals playing a certain strategy A index I. So the frequency, the fraction of individuals playing a particular strategy, is the number of those individuals divided by the total population size. Okay? Now, the way you update the dynamics, we update the population, is you just apply certain evolutionary rules. And they can be very complex. They could be deterministic rules of updating. They could be stochastic rules of updating. They involve all kinds of interaction between the individuals, which could be direct or indirect. They could be discrete in time, so you would have time steps and generations, or they could be continuous in time. So you have the whole range of mappings from one situation to another situation. And from that you immediately see what that kind of game theoretical setting amounts to. It amounts to studying populations as a function of time, where you have stochasticity entering and non-equilibrium and nonlinear effects entering by the type of interactions you have between the different strategies. Okay? So a typical setting, which I'm going to allude to in the next few minutes, is the deterministic well-mixed scenario. So what does deterministic mean? I will assume that the number of particles or individuals of a certain type I is macroscopically large, much larger than 1. And well-mixed means that I'm putting the diffusion constant essentially to infinity, so everyone is seeing everybody at the same time. That then is depicted in what's called a Moran process or an Earn model. The idea is as follows. You have here 3 different strategies, blue, red, and yellow. And at a given instant in time, you randomly pick 2 individuals and let them interact by the rules given by the game. And then the one winning, here the red one, is replacing the blue one, such that the total population size is kept constant. That's how the game is formulated. Okay. Now the question you have to ask is, once you have a formulation of a game like that, how do you come up with a dynamic equation. And there are two ways of doing that. There's one way which is actually very simple and obvious. It's when you can describe the reactions by some kind of chemical reactions. So let's look at this Rockscissor paper game where the rock is smashing the scissors is cutting the paper, and the paper is wrapping the rock. Here you have the obvious dynamics that if A meets B, it dominates over B, and it replaces the B by an A with a certain probability per unit time called a rate Ka. And the same kind of reaction applies cyclically for all the other remaining species B and C. So these are, as I wrote them, chemical reactions, and you immediately can turn them into rate equations. They read like follows. The temporal change of the fraction of A particles in the system is a gain and a loss term. You gain if A meets a B, that happens with the probability of fraction A times fraction B, and the change comes about with the rate, the probability per unit time given by Ka. You lose particles A if A meets a C, probability is A times C, and the rate of change is given by the rate constant K. So this is pretty simple and obvious, and you have this set here of equations. And you now see immediately, this is a vector ABC, and this is a function which has vector values. So we have a nonlinear dynamics, and what you need to study is the behavior of nonlinear differential equations. In the other setting, where you would have a payoff matrix, you first need to translate payoff into dynamics. And there is, of course, a debate how to do this. This is not in no ways unique. You have to make a choice here. In the way people choose to do that is, so they look at the payoff matrix, which you can also write as a real matrix with entries Pij. You see that you have frequencies, which is the relative number of A particles and B particles, and as I'm considering a fixed population size, the fraction of B particles is 1 minus the fraction of A particles. Now, you translate the payoff into fitness by saying that the fitness equals the expected payoff, and later on the fitness will be proportional to the growth rate of your species A or B. So the expected payoff is simply written down by multiplying the frequency of a particular strategy, A, by the payoff, which would be here for player A, the reward times the fraction of players playing strategy A, plus the sucker's payoff if your opponent is actually betraying you and is playing the other strategy. Similarly for B, and then you define what is called the average fitness, which is just the fitness of strategy A and B with a weight given by the frequency of individuals A or B. So that's the definition of fitness. And now I say I use that definition to write out a dynamic equation, and I say that the growth rate of a particular strategy is given by the surplus of the fitness as compared to the average fitness. So what I do here is I say the temporal change is the fitness of individual A compared to the average fitness multiplied by A. That's a very simple equation. It has a name. It's called the replicator equation or replicator dynamics in game theory.
Always, as you said, it's somewhat arbitrary.
Totally.
It's basically assuming everything is linear and
Exactly. And we will see a biological example where this here actually is not true. It's an assumption which you make and which can be done in a particular setting. So you have to think about it. Okay?
So that the linearity is similar to what I will point out in the sense that there's no saturation. I mean, the more fit you are, the
there's saturation, there's saturation here because I'm considering a fixed population size. So if you win against somebody, the other guy is taken out of the population and replaced by the winning individual. And that keeps the population size constant. That's so to say a canonical ensemble where you keep the particle number fixed. If you would allow for dynamics of the population size, then you would need in the equation of motion, so here, a term which takes care of the finite carrying capacity. And then you would have fluctuations in the total number of individuals. But in the end, log Volterra also goes to sometimes to oscillation.
Can you restate the physical meaning of FAA and FB?
I said, this is the fitness of player of type A. And this is the fitness of player of type B. And the way you define the fitness is by averaging over your payoff given the frequency A or B of your opponent. That's the definition. And as Uwe pointed out, that I put this here linear in A or linear in 1 minus A is my choice. This could be different.
Linear in R and S.
Lots of things. In particular, I think the most important thing is here dependent on A, because that's the dynamic variable, and that determines what kind of game you get. And if you do it this way, then you get 4 types of scenarios for the 2-player game. Is that clear? Good. There's a different way of putting the dynamics. I said I would choose the growth rate as the deviation, the surplus, with respect to the mean. You can also say you take the relative surplus and divide by the mean. Again, this is your choice. There's no way to say this is defining a particular biological or physical situation. Okay, now after talking about these game theoretic aspects, let me come to different biological settings to just show you that there are instances where these kind of game theoretical problems play a role in biology. Here's a quite classical example of a game theoretical problem in population dynamics. So this is about lizards in the inner coast range of California. Those are small guys, about 5 to 10 grams. And they have been observed here over a time period which was from 1990 to 1995. And what people observed here is the relative frequency of differently colored lizards. Those lizards, they are different by their throat color. There are guys with an orange throat color, with a yellow one, and a blue throat color. And this throat color is linked to their strategies of finding females. So, there are 3 different types of finding females and keeping them together.
So Erwin, only the males have different colors?
The women also have different colors, but not all. I'll come to that in a second. If not, please remind me. But it's mainly the male who have different colors, and the color tells you what kind of strategy they play in finding them. So the orange throated lizards, those are very aggressive guys. They try to have as many females as possible and have a huge harvest. The blue-throated lizards, they are more on the conservative side. They would be satisfied with a smaller group of females, but they would be very careful about taking care of them, protecting them. The yellow-throated are sneakers. They don't keep a territory. They just sneak into the other's territory and try to find what is a female they can get. Okay, so you have here 3 different strategies, and you have to ask yourself, how are they dominating each other in a relative way? And it's kind of clear the aggressive strategy dominates over the more passive strategy, by sheer power, I would say. Then the yellow guy here, which is sneaking in particular picking out women with the same kind of throat color. This guy has a lot of chances to sneaking into the territory of the aggressive lizard, since he's keeping just such a large territory and not taking care of his females, then it's just easy for him to find one. Whereas the blue throated lizard is, of course, guarding his females and careful enough not to let the yellow lizard in. So you have a cyclic dominance, like in a Rockscissor paper game, and actually what people observe when they look at the relative frequency of the different morphs here in the population, they find oscillations as you would expect if you would analyze this Rockscissor paper game as I wrote it down just 2 transparencies ago.
So how come the gene for this behavior is related to the throat color?
Ask me, I don't know.
So it looks like the oscillations are damping. Is that
They
right?
are damping, that's true. That's true. That's what they observe also. They don't give an explanation for that. And if you think about this in more and more detail, you realize it's very, very hard to analyze. Because there's a lot of question about how you take the data, what the influence of the environment is. There are many, many, many open questions. And it's not really well suited to analyze population dynamics. It's a real problem, so people would like to understand it from the perspective of a physicist trying to understand mechanisms in the biological system. This is not a good system. The better systems are bacterial systems, and those are the ones I'm talking about in the next few slides. Okay, this is just what I said. You can map this on a Rockscissor paper game. And instead of playing this beer pong, I would suggest that you try this in the evening. I can hand it out later. It's an advanced version of Rockscissor paper. It needs some intelligence to keep a memory of all the interactions. So, now my global laboratory communities. These communities are really the model system for understanding evolutionary dynamics in the biological space. And there are more and more groups worldwide concentrating on these kind of systems. And I think this is really a tremendously growing field where a lot of opportunities are experimentally as well as theoretically. So let me give you 2 examples which I think stand out. There's one example which will be the guiding principle for what I'm going to talk about in the remaining lectures. This is so-called polysogenic bacteria. It's a strain of E. coli. And this strain of E. coli is producing a toxin called colicin. In order to do that, to produce that toxin, it needs a plasmid. And this plasmid carries the gene for producing the toxin, but it also carries the gene for protecting the individual against the toxin. That's an effort it needs to make. Then there are sensitive strains. They're simply killed by the toxin-producing strain. And there are mutations in the population. And these mutations in the population, they became resistant against the toxin by a mutation of a membrane protein, which is responsible for the take-up of the poison. So they no longer take up the poison, that's why they're resistant, but they pay a price. Those membrane proteins are also responsible for nutrient uptake, so they have less nutrients they can take up, so they grow slower than their competitors, which are sensitive to the toxin. And that together again gives a cyclic dominance as follows. The toxin-producing strain kills off the sensitive one. And as I said, the sensitive one outgrows the resistant strain because the resistant strain is lacking the membrane protein, and that's why it's growing at a slower pace. And finally, the resistance strain is actually outgrowing the collision-producing strain because it's not paying the cost of having all that machinery here for making the toxin and protecting oneself against the toxin. You can measure that. You can look at the different strains and grow them individually, and you see that what I just said is true, and that the growth rate of S and R and C are such that we have such a cyclic dominance. So this is the situation. This is again the Rockscissor paper game, and here are the data which were taken by Benjamin Kerr some time ago. He did the experiment in two different settings. One setting here is shown on the right corner. This is a flask, so it's just a container which is constantly stirred, and that means you are in a well-mixed environment where everyone sees everyone at the same time. In that well-mixed environment, the outcome is that one strain here, the blue, which actually is the sensitive strain, dies out first, then the toxin-producing strain dies out, and what survives in the end is only the resistance strain. And that happens as we repeat the experiment time and time again.
So that's because in the Rockscissor paper game, it is not quite the Rockscissor paper game because we have different rates there, right? So
yes, that is. I can talk about this later. There are many reasons. There are many reasons why that happens. That's one of them. I would need time to explain that in more detail. But as you say, the reason is you have asymmetric rates in the Rockscissor paper game, and on top of the asymmetric rates, you need stochasticity, because otherwise you are on orbits and you periodically circle around the orbits, and the stochasticity then pushes you to some absorbing state, and the game is over.
Nice and small numbers here.
Yeah. I will explain that. That's one important outcome of the analysis. The second scenario is very different. Here the game is played spatially on a Petri dish, as shown here on the left side. So you have a random initial condition at some point in time, where you place collision-producing bacteria, sensitive one and resistant one, randomly on the Petri dish. You watch them over time, from day 3 to 5 to 7. And what you see here is the domain boundary between C and S, here in yellow, moves downwards. So toxin-producing strain is conquering the area of the sensitive strain, and at the same time the domain boundary between C and R, the resistant strain, is moving the same direction. So you do have the cyclic dominance of one species chasing the other, chasing the other. And the outcome then is, over the time period they have observed that, is that you don't lose the diversity in the population, you maintain the diversity in the population, all three strains survive. And I would like to explain both scenarios. And to explain both scenarios, you need a lot of interesting non-equilibrium, non-linear physics.
So, in the case where you have them spread out on a petri dish, yes, they all survive, but the populations definitely migrate in a reasonably well-defined way. Is that true?
Here, you would like them to migrate with their flagella. That would be the ideal situation then, because then you would have quite a significant mobility in the population. Here it's more or less diffusion, I would say.
Well, no, I mean the population boundaries.
What
the boundary between the different populations migrates in a reasonably well-defined way.
This is just growth.
Yeah.
You just grow, you kill S, and you grow into the area of where you kill species S. Just by growth.
And so the resistant strain doesn't grow into the area of the...
It does.
Yeah, so so you can think of modeling the boundary in the diffusion of the boundaries.
You could now model all the details of the mechanics of bacteria and how they interact, etc., etc. I won't do that because you don't need to do it. I'm interested not in the details of how the domain boundary moves. I'm trying to understand why is there such a biodiverse state. Okay? So it always depends on the kind of question you would like to ask in studying those kind of systems. Of course, there's room in asking about what's the pressure generated by bacteria as they push against another population. What is the physical mechanism of domain wall movement? I won't go into that. It's a valid question which one could ask. Yes?
So presumably these bacteria are also dividing as you're measuring, and these strains will be divided at a different rate.
Yes.
So how are these different rates normalized or taken into account in these three?
They are not taken into account, they just take the strains they have. They measure the strains, so they determine the growth rates so that they know what the growth rates are. But once the growth rates are kind of measured, you can't vary them. What you would need to do is you have to mutate those guys. Right? You put in, sometimes it even helps to make them different colors. So you put in a green or yellow fluorescent protein to make them light up, so that you can watch them experimentally, and that has an influence on their growth rate. But for a given strain, the growth rate is not a variable. You cannot change it. What you could try to change is the mobility. That's easier to do because there are different substrates. There's soft agar, there's hard agar, there are bacteria with flagella, without flagella, etc. So that could be varied in a more or less controlled way. And remember, the dividing rate of bacteria is 20 minutes. That's a long time. So if you want to have a time series which is reasonably long as compared to a theoretical studies, you're talking about a month, which you would like to observe. Here this is just a very short cut in the dynamics of that bacterial strain.
So are there experimental results for higher mobility?
We are trying right now to have strains where you would have mobile bacteria with the flagella on. Mm-hmm. The problem is once you make the agar soft, then it's fluid, and the poison is unfortunately spread all over the place, and you kill everyone.
Okay.
So there are tricky issues with the experiment.
Right. So would you say if you could do that and increase the mobility, would you expect that the static situation would be more like the well-stirred one?
Yes, that's what I would expect, and that's why we made a theory.
Okay.
Yeah. Another question?
I think that just answered it.
Okay, good. So the next is cheating in yeast. This is a recent set of data from Jeff Gore in the Udenam lab at MIT. So what they managed to do is to look at yeast here, and there's the following situation. Yeast likes to feed on a certain kind of sugar, namely glucose and fructose. Favorite food. But sometimes you don't have glucose and fructose available, you only have sucrose. If that's the case, then you need a machinery within the yeast which transforms this kind of sugar in the other type of sugar. That's done by a so-called invertase enzyme, which does the job of converting sucrose into fructose and glucose. For that you need, of course, a gene which produces the protein, and some of the yeast cells, they do have that gene and the invertase, but others don't. Another situation is the following. The guys having the gene and having the invertase, they transform the sugar into one everybody can eat, but they're very selfless. They only take 1% to themselves and spread 99% to the environment.
So the invertase actually works in the outside?
Yeah, it works in the outside, and create a flow of sugar in the outside. It could do it in the inside, but it doesn't. So it's a pretty cooperative individual here, working for the others. Then there are cheaters, of course, missing that particular gene, so missing the invertase. They're just eating. They take advantage of the cost these guys are paying and just reap the benefit. This looks, from what I said in the beginning, very much like a business dilemma.
What's history?
Okay, history comes to the story later. I can talk a bit this now. So, in the business dilemma, you have benefit and cost. And in order to analyze a game, you would like to have a knob to turn the benefit and cost. The his here is the following. This guy feeds also on histidine. And by regulating that, you can change the benefit or cost factors in the game. That's why you need that. So it's an additional knob to change control parameters in your system.
Can you also play the game with one that has the invertase on the inside of the membrane?
Austin, I don't know how to do it. I mean, you cannot easily engineer those guys totally. You can engineer things like switching off a gene, switching on a gene, but really to engineer such that a gene with all the inside machinery would put the invertase not on the outside but on the inside, that's something which is very hard. If you're lucky, you may be able to do something like that. But typically it's on-off. On-off or change levels of certain protein production.
Did the cooperator evolve to be so wasteful, or was it engineered to be?
It is like that.
I'm sorry?
Yeah, it is like that.
Okay, is there a reason why it's spent 99% of its time giving?
It's not engineered, and it is like that in a university population. There are so many strains of bacteria in different places in the world at universities, and they have been there since 10, 20, 50 years, so they have evolved. And they're different from the yeast you use for beer. But essentially, it is like this.
Yeah. I was just wondering if there's any evolutionary reason for it to be doing that.
Maybe there is one. We come to that.
Okay.
Maybe it's just difficult to get sucrose in whole.
Cannot answer that.
It's too big.
Yeah. What's the reason?
You can't make sucrose when it's too big.
Okay. Good. Thanks. Now, this is the experiment. So I hope you got the setting now of the experiment. Here on this axis is the fraction of cooperators, and here is time. So let's look at those two graphs here. The upper situation is at time point equals 0, you start with a population set such that you have only cooperators and a minute amount of cheaters. So what they observe is that the fraction of cooperators goes down. That means that strategy is not evolutionarily stable, but is invaded by cheaters. Now look at the lower panel. The same is true in the opposite scenario. If you start from cheaters only and put in cooperators, they are also invaded. So it seems it's always better to do the opposite of what your opponent is doing, right? So if all people are cooperating, you better defect, and vice versa. So that looks like a Snowdrift game. The question is why? Why is that a Snowdrift game? Here, that panel here shows the fraction of cooperators over a longer time, or put the parameter such that you could see the saturation over the time window where you observe your population, and you see that there's actually a finite fraction of cooperators developing after time. And now come back to the his gene. By changing the his here, you can change the benefit, and by that you can change the fraction of co-predators in your population, and you have a knob to see what the equilibrium concentration of co-predators is depending on their cost of benefit. Okay, now how to explain that, because looking back at this and formulating that in terms of replicator equations in a linear fashion won't work. It will give you a Christmas dilemma. So the way out, the suggestion they make is the following. Instead of writing the payoffs now for the defectors and co-predators in a linear fashion, F now is the fraction of co-predators, epsilon is the amount of stuff which you keep to yourself, and 1 minus epsilon is, so to say, the benefit the others reap in the neighborhood. So this is the usual payoff then for a prisoner's dilemma game in a linear setting where you just multiply the fraction of your individuals by the benefit and cost. And this would give you this typical scenario where you would have, depending on benefit and cost, well, remember I said when the benefit is larger than the cost, you end up at the prisoner's dilemma. Otherwise, you end up what is called a mutual benefit situation where all co-predators survive. So they suggest that instead of that particular payoff matrix, you actually need to use a nonlinear version of it. And in that nonlinear version, the dependence of the payoff on the frequency of the co-predators as well as on the amount of benefit you reap by the sugar is a nonlinear power, some alpha, which they determine experimentally. And they can do that, and by doing so, they can map out then a phase diagram in terms of efficiency and cost, and they find that their population is in this intermediate regime where they have a Snowdrift game with the alpha value, which is something like 0.3. Good. So that's what they find. And I think it's important to keep in mind that there are these types of generalizations of game theory and settings which are important if you want to do a real biology.
It's just, I missed it. SG means
Snowdrift game.
Snowdrift game, okay.
So this is mutual benefit, Snowdrift games, and prisoner's dilemma. And I didn't really go into describe this in detail, but what you would need to do is you need to take this payoff matrix, you write down the replicator equations, those are nonlinear equations. You can analyze those nonlinear equations for their fixed points, and you will see that in this parameter regime, the fixed point is 0 co-predators, so you are in the prisoner's dilemma. In this parameter regime, the fixed point is 1, so you have all co-predators. And in this regime between the black curves, you have a bistable situation such that you have a finite fraction of co-predators.
And that's still believing the rate equation.
That's, of course, they make sure that they have a well-mixed, there's a setting there where they have all kinds of pumps to keep the population size constant. They stir it well, so I think that's safe, that assumption that they are in a well-mixed situation. The number of bacteria is also very high, so you can analyze this in a deterministic fashion. And this, of course, is an ansatz they make, and they determine the exponent alpha by comparing with their data, and that gives a consistent picture of their experimental results. That's as far as I can go. Yeah.
You have to seed one population or the other. There's no mutations that can bring you between the two.
Yeah, you have to seed it. Mutation rate is way too slow. We're talking here about days. This is an extremely short time scale on an evolutionary scale. So what you do is you just seed it and then see what happens.
Okay, so it's really it's ecology, not evolution.
Yeah. So it's not evolution.
Yeah.
I mean, people are trying to make long-term experiments where it's actually tricky because you need to keep a generation of bacteria over years fed such that they survive. And in order to do so, this is tricky, but people are doing it. People are making 20-year scale experiments on the evolution of bacterial colonies. And there are more and more people trying to do the same thing in the spatial setting now. In the spatial setting, it's really tricky because you need to generate an infinite system, right? So, yeah, so, I mean, ideas are welcome to generate that. Maybe a row, I don't know. Yeah, please.
So, what does the MB stand for?
Mutual benefit. Mutual benefit. This is when in the payoff matrix the benefit minus the cost is actually not positive but negative.
Okay.
Yeah.
Is there a physical reason for this concept, or it's just total guess?
Total guess. They're arguing, but I think it's a guess. It's a reasonable guess, right? Or reasonable in the sense that if you have a small fraction of stuff around which you can take advantage of, then the machinery you have inside the cell, there's no reason to assume that this is working linearly. So an ansatz of that being a nonlinear function is always generic. A linear one would be an exception. Right? So that's why it's reasonable.
This is about the quadratic fraction as a function of time you just showed in the previous slide.
Say it again.
This is about the quadratic fraction as a function of time.
Yeah.
So what is the mechanism for a cooperator to become a cheater? Because does the invertase that's inside the cooperator, does it last out, or how does a cooperator become a cheater? Or
they don't change their identity. They just become more or less. Just the frequency changes. So they have a chemostat where they keep the population size constant, and if the cooperators grow faster than the defectors, then the relative fraction of cooperators and defectors changes in the population. That's what happens. So you don't change the strategy, you just get more or less.
So how do they get more? Do they divide or what?
Yeah, of course. Yeah.
What's the value of alpha that they find?
0. I'll tell you later, but it's something like 0.3 or so. Yeah, I don't see that. It's a fat matrix. Yeah. Yes?
Is this alpha by any chance related to the underlying kinetics of the enzyme?
It's of course related to the whole machinery.
No, yeah, okay. But
and it's a coarse way of lumping everything into one factor. Yeah. I mean, these models are not the truth. They're never true. This is just a way of thinking about the system which is consistent with the data. Okay.
Yes. Seems to me that this would work quite differently if you did not restrict it to a constant population, because essentially what the cooperators do is increase the total available energy supply. And so if you didn't restrict the population, I would expect the total population to rise.
Yeah, very good point. You're right. It's interesting to study that. Okay. So I think I'm done with my time. Right? Because it doesn't really make sense to start this now. This is a 10-15 minute thing, and I would rupture it apart. So then
There's just two more questions.
Yeah.
Right. Okay. So more questions? working?
So can we go back to the work from Kerr from 2002? In the case where they did the static plate, they're using non-motile bacteria, or are they using one without flagella?
It's non-motile. They have no flagella.
Okay, so the only thing that can cause injury pushment.
The only thing they can push the domain, the domain boundary forward is by growth into the region of the other species. So physically, they're just generating more of their own type and then mechanically push into the other region.
I see.
So by growth.
I see. So in that sense, you're working in a zero diffusion coefficient limit, and so you would expect that
exactly
until you reach a time scale where everybody can see everybody else, then you would expect to have a static.
You're not quite right that it's zero diffusion constant. It's almost like that because you have no explicit swapping of neighbors, but by changing your site, even if you're growing, you're generating something on a large scale which looks like a diffusion contribution in a diffusion reaction equation. So, but it's certainly on the lower side of diffusion. It's really the opposite of the flash geometry.
I see. So you would expect that if you ran the experiment for a ridiculously long time, then you would expect to see the same behavior.
No, I would not. I would not. I will argue for that. For that, I need some theory. If you would run this for infinite time, then you would see that. But if you would run it for a time which is smaller than the population size, of the order of the population size, you will not have a situation where things die out, but where you maintain biodiversity. See, in those situations, you have an absorbing state, right? So it could always happen by chance that you have one species playing against the second species and the third one not being there. And since you have dominance of one or the other, this automatically drives you towards the absorbing state. So that means mathematically or physically, there's a probability of 1 in infinite time to reach the absorbing state. The real crucial question here is, how does that time scale to reach the absorbing state scale to the system size? And my argument later will be that as a function of the diffusion constant, the scaling of the extinction time with population size changes dramatically at a certain critical value of the diffusion constant. So you need a diffusion constant above a certain threshold to go into a regime which in the long time scale limit, the asymptotic limit, is effectively a well-mixed situation.
And this hinges on starting from basically a random distribution. If you ordered your distribution of your species, you would see something very, very different.
Yeah, that's another feature of these non-equilibrium nonlinear systems. There is quite a significant memory of the initial state on the final state here. And that also comes out, if you look at the math of it, there is a memory, a very strong memory on the initial state. If the initial state has a variation in density whose amplitude is larger than the effective noise you have, which is generated by the stochastic processes of selection and reproduction in the system. So there's an amplitude question about what is larger, the initial variation or the noise in the system.
And do the experimentals have a way to tune the noise in the system?
Yeah, of course. A simple way. The noise here is no temperature. The noise here is the finite population size. So a small population size is large noise, and a large population size is small noise. You will see that. That's very interesting, right? Because you can change temperature, so to say, in the system by changing population size, in a way. Yeah.
It's hard to get to a regime where your mutation time is on the order of, or your time is on the order of the ecological time. Have anybody tried to play these with invaders? Just throw in some new or some changed organism at some time scale and see whether they take over or not.
I thought that's what they're doing in those two situations. They, I mean, it's yeast, two different strains of yeast,
right?
But they had a population of all cooperators, and they would throw in defectors and see what happened.
Right, but then throw in a third one.
Yeah, I mean, lots of things can happen there.
Yeah.
I think the really crucial thing in those bacteria or yeast populations is that you well characterize your individuals first, and then you ask a specific question about the system as a function of time. Just randomly, mixing things together can give you something. I mean, Bob Austin, we heard yesterday, is a very creative guy, and he did that. He just took a labyrinth of some microfluidic array and put in lots of stuff, very uncontrolled, and he observed lots of interesting phenomena, but you don't know what's happening.
Right. No, I'm asking because I'm interested in the limit with the evolutionary time scale and the ecological time scale are not so different.
Yeah, I mean,
fishes or...
Yeah, I mean, people are trying. I mean, there are examples where evolution is past, and you can play this ecologically and evolutionary time scale are similar, but still, these are tedious experiments, which you need to run for a relatively long time. And relatively long means always longer than a day. Right? You would like to finish an experiment in a week or so. Otherwise, just having trouble, keeping students. Yeah, system gets unstable.
In the top graph, it sort of seems like the red species is below the blue species, below the green species, but they're all pretty close at the same time. So should I take any stock in that, or will those lines cross if you were to?
Don't take this as highly averaged data. This is one shot. Okay. This is one time series, and it looks actually rather smooth for one.
It's on a long scale.
It's on a long.
Long.
Exactly. So it's actually much wilder than what it looks like. Thanks for noting that. And it should look random. It's a random. It's a stochastic experiment. It's one realization, and ideally we would like to have many realizations.
But it's a zero-sum game.
It is not a zero-sum game.
No, in the sense that it's constant population.
Okay.
Population.
Yeah. But it's not a zero-sum game in its definition.
For the use game, if there was a true prisoner dilemma, would all the use die out essentially? Because the humans would take over and then it would be having a triggering situation.
Yep. That's the problem with all social dilemmas, right? If the guys taking advantage of the other ones are taking over, they don't have anybody left to do the work. And it would be the case. I mean, yeast would die out because it could not feed on the sucrose.
So when you say Snowdrift game, right? Is there in this case you were talking about the dynamics, right? That it just flows under the dynamics the way you would expect a Snowdrift game in the linear regime. Can you convert that back into a Payoff matrix, or is it just more of an analogy?
It's an analogy in terms of the biostability of the system, and there it becomes. But if you put things in terms of math, it's more obvious what a Snowdrift game is. In terms of a nonlinear equation, this is a one-dimensional maybe this way. In the equation you have is d2a is some function of A. This is the fraction of co-operators, and the right-hand side is all the stuff you collect from your payoff matrix. So this is a one-dimensional nonlinear problem. Then you have several choices. You could have a situation like this, where your function f of A has this structure. Then here the function is positive, so the flow goes this way. Here the function is negative, so the flow goes that way. That means this is unstable and this is stable. That would be a situation where you have all co-operators that mutual benefit. The prisoner's dilemma is just the other way around. Here this is negative, the flow goes here, so this is stable and this is unstable. That's prisoner's dilemma. And finally, if you have a situation like this, do I put this right? No, wrong, sorry. So here, oh, wait a minute. This was right, actually. Sorry. This was right. So here you have 1, and here you have 0. And now you see here that's positive, so the flow goes this way. Here it's negative, the flow goes that way. And that you get a fixed point, which is in the interior, not between 0 and 1. And that's what's called a Snowdrift state. And in that sense here, the nonlinear problem is this. And if you think of this in terms of this nonlinear dynamics, then those are the only scenarios you have in a one-dimensional setting. It becomes more complicated if you would have more species, but for one species or two species with the population constraint, that's it.
Can you then convert from the derivatives of A or something, those things back into a payoff matrix? Let's say, a pseudo payoff matrix, I guess an effective payoff matrix, linear order. So.
You can always linearize around the fixed point and compare the linearized version of your nonlinear problem with the linearized version of the linear version and math parameters. I think you can do it.
Okay. Okay, just conclude our morning session.